Hi, welcome to our next installment of our archaeoastronomy lessons. Today we're going to focus on the sun. So to put it all in context, the sun is literally the light of our lives. We know that the heat we feel on a summer's day comes from a distance of about 93 million miles or 150 million kilometers. And if we compare that heat to that of a nearby bonfire, solar energy is literally astronomical. The sun's heat draws up water from our oceans and drives our weather. Its light enables plants to grow our food. Our very lives depend on the power of our local star, the sun. So, the role of the sun in the Neolithic period wasn't too different than the role the sun plays in our lives today. But observing the apparent movement of the sun became particularly important when people began to settle and adopt an agricultural way of life. Knowing what came next in the cycle of the seasons was vital, and knowing when to sow and reap crops, when to trade surplus crops, and when the crops needed to be rationed because we were entering a period of coldness and less light. This agricultural revolution occurred at different times in different civilizations, but overall it happened beginning in the Middle East in early 10,000 BCE, and Western Europeans were a little later to adopt this lifestyle, and that was around 3000 BCE. We call this period of time the Neolithic Age. When we look at Neolithic monuments, we actually see a lot of astronomical alignments to the sun, so much that we actually call this period the Age of Astronomy. But before we dive into those sites, I wanted to talk a little bit about the sun's role on the surface of our planet. One of the terms that's going to be something that you're going to hear from time to time is something called the obliquity of the ecliptic. So hopefully we all know that the Earth does not stand upright as it spins around the sun on its yearly orbit, actually leans slightly. This tilt is about 23.4 degrees from vertical. So this would be vertical, right? Our tilt is about this much. This is known as the obliquity of the ecliptic, okay? This tilt is measured from the Earth's axis, which is an imaginary line that runs through the center of the planet, connecting both the North and South poles and actually ventures into space. In the Northern Hemisphere, the axis, this imaginary axis, points towards the North Star, Polaris, making this star an important navigational aid. The tilt of the Earth's axis is constant throughout the year. This 23.4 degrees does not change. As our planet revolves around the sun, part of the surface is sometimes tilted towards the sun, while at other times the same area is tilted away from the sun, creating summer and winter respectively. So to kind of say it another way, just like imagine the Earth, right? We know the Earth rotates on its axis, but at the same time, it also has this weird tilt to it. So as the day kind of goes on, there's always going to be part of the planet that is facing more away from the sun, and there's going to be part that's facing kind of towards the sun. Another concept that is important to ancient astronomy is something called the solstice. So in the Northern Hemisphere, the day that has the most sunlight is on or around June 21st. This is called the summer solstice. In the Southern Hemisphere, this day is their winter solstice. The day with the least amount of sunlight, respectively, is the winter solstice. And again, in the Northern Hemisphere, this happens around December 21st. The nearer you are to the North and South poles, the more extreme is the relative difference between day and night at the height of summer and the depth of winter. And in fact, each pole has 24 hours of daylight, during the summer solstice and 24 hours of night at the winter solstice. Another concept we want to keep in our minds as we're looking at ancient sites is the equinoxes. So halfway between the two solstices is a day when everywhere on Earth, regardless of where you are, has equal periods of light and dark. These are the spring, often called vernal, and autumnal equinoxes. These dates vary each year, but generally they're around March 21st and September 23rd. And for those of you all curious why these dates vary, it's because our year is not exactly 365 days, it's slightly more. As you know, every 4 years we have a leap year, so we add an additional day rather than saying that each of our years is 365.25 days. But that difference, right, is not no one told the sun or the tilt of the earth, right, that we have one less day or partly less of a day. So the equinoxes kind of change in dates each year. The other thing to kind of bear in mind when we're thinking about the obliquity of the ecliptic is that many complicated systems are triggered by the fact that the Earth has a tilt. Global weather patterns are powered by the difference between summer heat and winter cold happening simultaneously on opposing hemispheres because the winds and the tidal current are in a constant state of trying to find equilibrium. And this mixing of hot and cold is what creates a lot of our weather patterns. Another phenomena, for those of you all interested, the aurora borealis or the northern lights is also affected by Earth's tilt. The most spectacular aurora occur around the equinoxes when the Earth's magnetic field links actually with the interplanetary magnetic field kind of surrounding a bigger area than just the Earth. And so a lot of the pictures you'll see of the aurora are kind of during that time. And also the aurora will kind of shift into different parts of the globe. So it won't just be at the poles you'll see it, you'll actually see it a lot more south or north based on where you are. That is the basics of understanding the Earth's relationship to the sun, as well as the Earth's tilt. Thanks for watching.